At 2:43 a.m., a global enterprise network accepted an AI optimization. No alarms triggered, no human intervention, and no visible error. Just a simple instruction: improve routing efficiency across backbone nodes. The system responded, accepted, but 9 seconds later, something strange happened. Nothing crashed, nothing disconnected, but traffic started behaving incorrectly. Not failing, not stopping, just quietly becoming unstable. And the log showed something engineers have never seen before. State valid, but not consistent. That's where everything started. Because systems weren't breaking, they were disagreeing. Most people imagine AI in networking like this. You install intelligence and everything becomes optimized. Clean automation, zero friction, and full control. But real enterprise systems are nothing like that. They are built from layers of history, including hardware from different eras, firmware that cannot be fully updated, hybrid cloud transitions that never finished, and system patched instead of replaced. So AI is not entering a model system, it is entering a time-fractured system. And that changes everything. Because AI thinks in real-time decision, but infrastructure was built for slow, fixed rules. That mismatch is where the first cracks appear. Inside large-scale networks, including enterprise systems built on architectures like Cisco-based environment, AI is already doing things like predicting congestion before it forms, rerouting traffic dynamically, dictating anomalies in milliseconds, and continuously optimizing network flow. On paper, this looks perfect, but in reality, something is happening beneath it. A conflict no dashboard clearly shows, because AI operates in milliseconds, but infrastructure updates in state locks, approvals, and constraints. So when AI makes a decision, the system does not fully obey it. It partially applies it and then creates something engineers now quietly recognize: silent failure zones. Places where nothing breaks, but nothing fully matches either. To understand the failure, you need to see the system in 3 layers. Layer 1, the decision engine, which is the AI. AI continuously generates routing adjustments, optimization strategies, and abnormality predictions. It believes the system is fully flexible. It assumes execution is instant. Layer 2, the constraint engine, which is the legacy infrastructure. Legacy systems do not adapt. They enforce fixed routing tables, locked configurations, compatibility rules, and stability-first logic. So when AI says, shift traffic instantly, the system responds, partial execution only, not failure, just limitation. Layer 3, where reality breaks, which is a conflict layer. This is where things silently go wrong. Example sequence: AI reroutes traffic globally. System applies 60% of change. AI next cycle assumes 100% success. Result: routing loops form. Packet takes conflicting paths. Latency spikes appear randomly, and logs remain normal. Everything looks fine, but behavior is no longer aligned. This is where the problem becomes invisible because nothing officially fails. Instead, systems oscillate between states. Optimizations override older optimizations. Abnormally, systems trigger false positivities, and routing decisions conflict with previous updates. And yet, dashboards still show status okay. So engineers face something new. They are not fixing failures anymore. They are interpreting inconsistencies. And that is harder because there is no single point of breakage, only drift. In production environment, this creates cascading effect. 1. Predictive routing failure. AI tries to prevent congestion, but partial legacy execution creates reroutes that don't fully apply, unexpected traffic bottlenecks, and repeated correction loops. So optimization becomes instability. 2. Abnormality detection overload. AI detects every deviation instantly, but legacy systems generate constant noise due to rigid behavior patterns, resulting to alert storms, ignored warnings, and reduced trust in AI systems. 3. Engineering role shift. Network engineers are no longer just operators. They are now validating machine decisions, debugging hybrid contradictions, and resolving invisible system drift. But the hardest part is this. They are not just fixing broken systems. They are aligning systems that never fully agree. Here is what most people misunderstand. AI is not failing, and legacy systems are not failing. Instead, AI is exposing the speed limit of infrastructure evolution because legacy networks were designed for predictive traffic, manual control loops, and slow update cycles, not autonomous decision-making, continuous optimization, and real-time adaptation. So the real bottleneck is not intelligence, it is synchronization across eras of technology. The next generation of networks will not be fully automated. They will be layered ecosystems, which includes AI handling optimization, infrastructure enforcing boundaries, and humans define constraints. An entire new roles will emerge: AI infrastructure supervisor, automation conflict engineer, and system intelligence architect. Because the job is no longer configuration, it is control of interacting intelligence. So, when AI recommends an upgrade and legacy systems appear to resist, nothing is actually resisting and nothing is breaking. Instead, two systems are running at different speeds with no shared definition of correct state. And that gap is what engineers now fear most, because it does not fail loudly, it fails quietly inside a system that will say everything is working. If you want more deep technical breakdowns like this, subscribe. Next video: why AI optimization creates problems that don't appear in logs.